correct something again. I do have this standard normal distribution table up here. We're not going to use it right this second, but whenever I do say, hey, y'all, look at the table, it's this piece of paper that's sitting up here by me, okay? Okay, so 5.1, just intro to normal distributions and the standard normal distributions. And like always, we have a lot of stuff to write, but I don't think that this is particularly hard. Like the words in writing it might be more confusing than actually doing the problems. I think once you actually start doing the problems, you see that it's not difficult. Okay? So what is a normal distribution? Let's go ahead and define that. Normal distribution is a continuous, random, variable, and has infinite number of possibilities, can be represented as an interval on a number line. I don't know if it's getting blurry or anything for you. It can be represented as an interval on a number line, and it is the most important continuous probability distribution in statistics. Okay. Statistics. I don't know why that word seems very hard to spell all of a sudden. She's doing it as well. Like that. I know. And you're always welcome to come to pictures of these too. The graph of a normal distribution, y'all, is called a normal curve. Okay, so graph is a normal curve, and then we're actually going to draw it underneath. It is not fun to draw. They're usually kind of ugly. They're not symmetrical. It's just on your paper. It's just a sketch. So don't be too hard on yourself, because if I was hard on myself, I would have skipped today. Made you watch a video. Graph is a normal curve. Okay, sorry. So just draw like a straight line. This would be your number line. And then you might hear it called like a bell curve, because it kind of represents like a bell. You're going to start on the left-hand side, and you're going to kind of go up, and you're just going to try to make it as symmetrical as possible. Honestly, put very little thought into it. That's the easiest way that I've been able to do it. Again, not perfect, not beautiful at all, but that's okay. Okay, so the normal curve itself, I'm going to define a couple of things down here. We're going to have a few bullet points. But let me just kind of fill out some things that are important pertaining to this normal curve. Okay. Right here in the very center, like the highest most point of this normal curve, of the bell curve, which would be approximately right here. This is our mean. Okay, so it's right in the middle. And then I'm going to kind of define to you that, the curve itself goes downwards in some places, upwards in others. Just kind of trust me. I usually go, I don't know what this would be, maybe half an inch to the right, and go ahead and do like a dash line going down. And then what I'll do is I'll put my pen here and I'll scoot over to the left just to try to make it as even as possible so that these two lines are somewhat equidistant. They're not. The one on the right looks like it's further. But just know the first dashes next to your mean. On the right hand side, this is your mean plus 1 standard deviation. So that's like that sideways 6 is kind of what it looks like, that symbol. So this is mean plus, and then a standard deviation. That's what I wrote there. It's just happened to be a lot smaller. Okay. And then on the left-hand side, that'll actually be the mean, but we'd be subtracting a standard deviation. We wouldn't be adding it, we would be subtracting one. And then we're going to actually go over again to the right and do more dotted lines, go to the left. We're going to do this 2 more times on each side. So about here, about here. This would be the mean plus 2 standard deviations, and this last one would be the mean plus 3 standard deviations. And then do the same thing on the left-hand side. And obviously my marker doesn't really allow me to write very big, so I'm kind of at an angle. But that's going to be your normal curve. So right there in the middle I have my mean, and then on either side of it I'm either subtracting or I'm adding a standard deviation, and then I do it again, and then I do it again. And we're going to do all the little bullet points about this normal curve. So with normal distributions, with this normal curve, our mean, our median, and our mode are all equal. Okay? Mean, median, mode, all equal. I've kind of used this word already, but we're going to say it again. It is bell-shaped and symmetrical. About the mean. And what that means about the mean, if we just kind of had this little normal curve cut out in our hands, we could fold it right at the mean, and both sides would be symmetrical. They would lay on top of each other. They would be exactly the same. Remember, our sketch is definitely not, but an actual normal curve would be symmetrical about the mean. It is bell-shaped, and very important here, it does not cross the x-axis. It approaches it. It'll get super, super, super close to it on both sides, but it will never cross. If you're looking at a normal curve, or they're asking you, is this a normal curve, and it crosses the x-axis, you would immediately say no, because it can't cross it. It approaches it, but it never touches it. Okay, so does not cross x-axis. Only approaches it. And let me go back to the previous bullet where it says bell-shaped and symmetrical about the mean. If you're on the homework and it's asking you, like, is this representative, of a normal distribution, and it's not bell-shaped and symmetrical, say it's skewed one way, you would say no, because it's skewed to the left, or no, because it's skewed to the right. Okay, so it can't be skewed either way, and it can't cross the x-axis. Those are very important things whenever we're talking about normal distributions and the actual curve. Okay. Also important, and we'll do more with this area of a bell curve moving forward today, but the total area under the curve, I'm sure some of y'all, bless you, remember, you're welcome, is 1. The total area under this curve totals to 1. Right now it just looks like a weird bump with dots and sigmas drawn all over the place, but don't worry about that, because we're going to actually put some numbers and stuff to it and it'll make more sense. Okay. And then this is a lot to write, but it is like one of the questions that they'll ask you, and it's pretty wordy, so I want y'all to have as many words as possible to answer it. So we're going to go ahead and write it, okay? Between the mean and then minus or subtract a standard deviation and our mean and adding one standard deviation. So between the mean subtracting a standard deviation and the mean and adding a standard deviation, that's right here. That's our actual mean. That's going to be the center of the curve. Okay. The graph curves downward. And let me go write all this out, and then I'm going to draw on the curve so y'all can see what I mean, okay? So between the mean and subtracting one standard deviation and adding one standard deviation, so right there, right in the middle, that's the center of the actual curve. The graph is going to curve downward. And then to the left, go and write all of this, and I'll draw my arrows. To the left of the mean minus one standard deviation, and the right of the mean adding one standard deviation, the graph curves upward. These are actually known as inflection points. So these are inflection points. In other words, it's where the graph changes direction. Okay, if it goes from curving upward to, oh, now it's curving downward, that would be an inflection point. And you're going to have one that occurs on both sides of your graph. And so right here at your mean minus one standard deviation, and then at your mean adding one standard deviation, I've got two dots that I've drawn there. It said between this point right here and this point, the graph curves downwards. So there, I'm actually going down. And then it said to the left of subtracting one standard deviation, so that's over here. And then to the right of the adding one, it curves upward. So your arrows would go like this. Definitely doesn't follow what we would think would be happening, but where it changes direction, those are called inflection points. And there might be like one or two problems on the homework. I really think it's more of like a definition where it's just gonna be really wordy and you need to know like which way things turn or curve or what it means to be an inflection point. The inflection points actually are going to be what tells us like where one standard deviation lies, either adding one or subtracting one from the mean. Okay. So means and standard deviation. There's one little, it's like a short page. And y'all, ST period D period is probably going to be how I start doing standard deviation. If I notice I have to keep saying it over and over and over and over and over again. Like when we do like the examples or something, I might do that. Okay. So the mean gives us the location of the line of symmetry because the mean was the center of the graph, right? And it's symmetrical about the mean. So wherever the mean is, that's the line of symmetry. So the mean gives us the line, the location of the line of symmetry. In other words, it gives us like the exact middle, okay, the center, the highest point of that bell curve. Okay. The inflection points, but we're going to call them the standard deviation. The standard deviation describes the spread of the data. And on the homework, it'll give you like these little curves. You'll notice some will be like, really kind of just real similar to the first one we did. And another one might go like up way higher. But your goal is just to look at the number line, look at the numbers, figure out where center is on your actual curve. And then what you'll do is, I believe it shows you your inflection points, and then that's going to be how you determine what the standard deviation is. So I've got two examples. It's just kind of annoying to like draw these curves, okay? So I'm going to kind of show y'all how these will look on the homework. Okay, so we're going to go ahead and draw one. Don't put much thought into it. I can't. If I do, I mess it up. So you see a curve, and it's like, what's the mean? What's the standard deviation? That's what it's asking you. There's like two little answer blanks, and that's all they want. Okay, so let me actually kind of put some numbers here to this. Because I know where I'm going, y'all, we need to go ahead and do the center of the graph, and on either side do the number 3 and 4, like that. We're going to have to kind of create it and then answer it, since I didn't print anything up. Okay. And then let's go ahead and do an inflection point right here, which will be like where our 5 is. And then right here, which will be where our 2 is. I'm telling y'all where everything is. The line of symmetry is right in between 3 and 4. One inflection point's right above 2. The other inflection point's above 5. And then you'll notice they have a few other numbers. I believe this is all you see, and it asks you for the mean, and it'll ask you for the standard deviation, and this is what we answer. So that's what we see, and this is what we answer. And you notice right above it, it says the mean gives the location of the line of symmetry. The line of symmetry is the highest point of your graph, right? The center of the graph. Again, remember, ours is not symmetrical per se, but it's going to be right in the middle. So I notice right in the middle on a number line that's falling right in between 3 and 4. So that would be 3.5. Our mean is 3.5 looking at this bell curve. What? Normal curve. Does that make sense? You find right in the center. Okay. Now the standard deviation is going to actually talk about the spread of data, and so what we do here is we look at the inflection points, and I told y'all where to put them, right? So right up on 5 and on 2. So if I'm at 3.5 and I go to 5, what is that difference there? 1.5 is the standard deviation, and that's how you answer that. I think there's 2 or 3 of those on there. When they get to the wordy, wordy problems, I truly think the only thing that's annoying is having to read the words. The actual math itself hasn't been bad. On these, yeah. On these, there's already on there. And then there's going to be some where it's like a paragraph and then you answer it. And, you'll sketch something just to kind of know where data points lie. And then that's it. Like, you'll see it's really not bad. People usually just don't understand any of what it's saying. Dominique. So, whenever I looked at this inflection point, it was right here at 5. And if I'm at 3.5 and I go to 5, its difference is 1.5. So 3.5, 4.5, and then plus 0.5 would give me the 5. So it's just right here. You could take this highest number, which you shouldn't have to do this. Okay, do this, Dominique. Say my inflection point was at 4. My mean's at 3.5. My inflection point's at 4. I went up 0.5. Right? Well, this one's at 5, so I went to 1.5. It's just the spread of the data. This next one, well, I think I pretty much just gave the answer with this one. Let's do this one, just so you can kind of see how they can look different. Again, right now it's just the annoying part of drawing it because I didn't print anything. Do your line. I'm going to make, it looks like that. Kind of looks like a ghost. Right? It's much taller and skinnier. We're going to have the center fall right in between 8 and 9. And we're going to have the inflection points be at 9 and 8. So if it asks me what's my mean, by the time you get to figure it out, the semester will be over. If it asks me what my mean is, I'm going to go and do a blue line for where my inflection points are. And that's where my bell curve just, changed directions. So my mean is right going to be here, which is the line of symmetry in the center of the graph, which I don't know why I was going to say believe, which I guess I believe is just dead center in between 8 and 9, which would mean the mean, according to this distribution, is 8.5. And then for the standard deviation, I look to see where the inflection points are. Where the inflection point is, like my standard deviation is not 8 or 9. Look at the spread of the data. The mean was 8.5. And then if I add one standard deviation to the right, I get to 9. So the difference between 8.5 and 9 is just 0.5. Okay, so it's just think about moving on a number line. And then I guess you could do 0.5. And that's it. Again, there's like 2 or 3 there. And they'd already you're not sitting there having to draw it and come up with stuff, and it tells you how I told you to recreate it. Okay, it already has the graph. And you'll see numbers on the bottom. It could be hundreds, it could be 87 and 88. You're just going to figure out what's dead center and then what's the standard deviation. Very similar to what we just did right here. Okay, moving on. This is where they actually kind of start getting wordy. Okay, so we have the empirical rule. Whew. I made that a strong energy today. Okay, the empirical rule. This is known as the 68, 95, 99.7 rule. Okay, so 68 dash 95 dash 99.7 rule. So the empirical rule, 68, 95, 99.7 rule is a shorthand used to remember the percentage of values that lie within 1, 2, or 3 standard deviations of the mean. And if you want to be accurate, you could put respectfully after that, because it's if your data lies within 1%, or like the value lies within 1%, one standard deviation, then 68% of the values are within that. 2 would be 95, 3 is 99.7. And I'm going to show you all what this means. So draw 3. So that we can have a visual representation of what this is saying. It is a shorthand though, because 68% of our data is going to lie within 1 standard deviation of the mean. So real close, like to the center, right? And then the further we go away from the mean, or the more standard deviations we go from the mean, the more data is going to lie there. So 68%. Let's do this. We know that all of our means are right there in the middle. And then if you start with the 68%, we have 1 standard deviation. This is plus a standard deviation. This is minus a standard deviation. 68% of all data lies right here in our normal curve. (95% of our data lies within 2 standard deviations of our curve. So here's 1 standard deviation, here's 2. And you got to do that on both sides, y'all. You can't just do it on one side. 98% of all of our data lies within 2 standard deviations. And then obviously, if the normal curve is representative of the distribution of all of our data, 99.7%, because obviously there might be outliers, right? As far as like how fast you drive, or bless you, whatever the acres is of the farm that this farmer sold, whatever the actual example is talking about. There could be outliers, but 99.7% of all of our data is going to lie within 3 standard deviations. So this is 1, 2, 3. 1, 2, 3. And then I honestly don't know. I don't remember if there was 3 or 4 of these for the homework. I did notice that both times I ended up kind of with a similar answer. I kind of wish I'd done another example, but I didn't want to erase anything or do a third one, so we're just going to stick with the 2 that I did. Okay, we're going to do these 2 examples right here. Okay, don't write this, but this is just an example of how wordy the homework is. It'll say that there's, cars driving on the highway with an average of 72 miles per hour and a standard deviation of 6 miles per hour. Estimate the percentage of people on the highway driving between, do you see what I'm saying? Like, there's all these words. The only thing I wrote down was what the mean was, the standard deviation was, and what we're estimating. You can pull those little bitty numbers off of the homework example, okay? So first example, we have a mean of 72. And we have a standard deviation of 6. And then what we're doing is we're going to estimate the percent between 66 and 78. So I just throw a little sketch up there so I can kind of see, well, where does 66 and 78 fall on a normal curve in relation to 72 being the mean. Okay? So if I do this, and I do this, and this is my mean, right? It splits it down the middle, and it's 72. One standard deviation to the right, I would be adding 6. What's 72 plus 6? 78, right? 72 is my mean. And then right here, this is, all we've been doing so far is just a little shorthand, right? Mean and then plus the standard deviation. Mean plus 2 standard deviations. I'm given the mean, I'm given the standard deviation. So if my mean is 72 and I'm adding 1 standard deviation, I'm adding 6. So 72 plus 1 standard deviation would be plus 6, which is 78. Now if I go to the left-hand side, I have the mean and I'm subtracting. Subtract 1 standard deviation. What's 72 minus 6? If you use your calculator, you'll get 66. And those happen to be the exact numbers that they asked me to find, right? Like what's the approximate percentage of data or people driving this miles per hour on the highway? And if you look, 66 and 78 fall both within 1 standard deviation of the mean. Oh, I hate it whenever I leave something off. These are percentages, y'all. I know I kept saying it, I just didn't draw it right here. It's 68% of the data lies within 1 standard deviation. 95% of the data lies within 2, and the 99.7 lies within 3. Okay, so if it asks me to estimate what is the percent between 66 and 78, I notice right here that this is what they're talking about, and those are both adding 1 standard deviation and subtracting 1 standard deviation, which means my answer is 68%. Okay? So it tells you, it says the word mean, and it says the word standard deviation, and then it tells you what to estimate. And then just kind of do a little sketch, and you'll see, oh, I screwed it over 2 standard deviations, or I screwed it over 1. Whichever one you screwed over, that's your answer right here. 68, 95, 97, 99.7, I mean. The next one, they don't just ask you to estimate the percent. I'm going to write down like kind of how I answered it. But the next one, they kind of give you a sample size. So we're not going to stop with, 95%. We're going to actually figure out what is 95% of that sample size. So that's like the only little difference there. But let me write this. 66, comma, 78 are both. Hello, how are you? Are both 1 standard deviation away from the mean. Therefore, approximately 68. I ran out of room. Percent. Mm-hmm. It's a little bit easier when you're here. Does that make sense, y'all? Just know, like I said, this problem, I literally pulled it from the homework, and it says, on the highway, there's people driving an average, right? Average is mean, right? An average of 72 miles per hour with a standard deviation of 6. Estimate what the percentage of drivers that are driving between 66 miles per hour and 78 miles per hour. There's my average. They told me my standard deviation. Do a little sketch. See where it lies according to our empirical rule of 68, 95, 99.7. And then you'll notice, oh, the 2 numbers that they gave me, they're between 1 standard deviation. Boom, answer 68%. Okay? Now this other one talks about like you're selling acreage and you're a farmer. Okay, and it'll actually tell you that there's like X amount of farms, like, or so many, like there's a sample size. So we won't stop with 68%. We're gonna actually see what is 68% of this sample size. Okay, let's go and write it all down here. And they did dollar amounts, so I went ahead and added the dollar amounts on this example. Say our mean is $1,700, and our standard deviation is $200. And then the difference here is that it has a sample size. So our N is 85. I don't remember the words. There's some farmer dude who has acreage and maybe his farm costs $1,700. Other farms cost, $200 more, $200 less. There's 85 total farms. All I care about is the mean, standard deviation, and the sample size. Now what we're going to do is we're going to estimate. 8% between 1,500. So I can estimate like how many farms, cost between 1,500 and 1,900. So I throw a little SketchUp. Just because it helps me see. I know that my mean was $1,700. My standard deviation is 200. So if I add one standard deviation to the right, what do I end up getting right here? 1,700 plus 200 is what? Yes, class, 1,900. And then if I subtract one standard deviation, so my standard deviation is 200 and I have 1,700, and I subtract 1,700, what do I have? One standard deviation to the left. I would have the 1,500. And whenever I did this example, I realized, what's the percent that I'm in? I'm both of my values lie within one standard deviation of my mean. And so I'm dealing with, again, 68%. But the difference here is because they gave me a sample size. Here, let me just figure out how to write this down here. 1,500 and 1,900 are one standard deviation away. Therefore, 68%. But you don't stop there because I actually have a sample size. What I need to do to answer this question completely is figure out what is 68% of 85. And the way you do that is you take your n and you multiply it to 68% turned into a decimal, so 0.68. Of, in math, means multiply. So what is 68% of 85 farms, or 85, whatever the homework problem is talking about? When you put that in your calculator, you're going to get like a decimal number, and you'll notice it tells you to round to the nearest whole number. Okay, so what you get should be 57.8. But if it tells you to round that to the nearest whole number, how many farms or how many whatever am I talking about? 58. What's up, Dominique? You look like you had a question. First question, there's no n. So it's just, where does it lie here? That's it. Second question, they actually give you like a sample size. So it's not just approximately, how much of this data is, are we talking about? It's like specifically, right? Once I figure out that it's one standard deviation, I'm dealing with 68% of the data, I need to figure out what is 68% of that n. Because they gave me the n, that's the only reason why I got to do that little multiplication right there at the end. That's the only difference. Because both 1,500 right here, this was the mean minus one standard deviation, and then the 1,900 was the mean plus one standard deviation, which is the 68%. Now say they told me to estimate the percent between $1,300 and $2,100. What? I'd have scooted over one more standard deviation. I would be highlighting a little bit more area. Now I'd be dealing with 95%. So then the last step I would do is, what's 95% of the 85? It just happened to be both examples. I was 68%. And I just didn't change it. I could have, but I didn't because I don't know. I just didn't. Does that kind of make sense though? Just remember, they're a little bit more wordy. There's cars driving on the highway or someone selling something. It's like a farmer selling acres. I don't really remember. But the important thing is, what's your standard deviation? What's your mean? And if there's an end, you got to do this little multiplication right at the end. Okay, that's the only difference between these two problems right there. Okay, so let's talk about z-scores. Y'all, come grab, I don't think we need it, like, right? Yeah, maybe, probably. I'm trying to look. No. This is like computation by hand. We're gonna need this little table up here in a minute, so if you don't have it, I'd come and get it. Just so I'm not talking about it, and then you notice you ain't got it. And if you keep these and you have them on the test, fine. If not, I'll print more up. But these are really important. It actually does a lot of the math for you. This is gonna be like how we're gonna end up finding the area and stuff. You got one, Dominic? Do you have one? Like kind of table looking, yeah. Yeah, no. I'd like to think in your life you'll hear that word again. Maybe not in a mathematical sense, but okay, yeah. The standard normal. The standard normal distribution. We got a few different things to talk about here. It is starting the area of these bell curves, or how do I keep calling it a bell curve? It's a bell-shaped normal curve. Okay, so the standard normal distribution. I just kind of want to point out something, just so nobody's like, hold on, like, how is she not talking about the same thing, and like things are changing. We just did the normal distribution. Okay, you got the mean in the middle, add a standard deviation, add 2, add 3, subtract 1, subtract 2, subtract 3, right? This is the standard normal. So that's like the main difference. Like the name changes there, and then that's why everything else kind of changes as well. Because now we're kind of talking more about area. Okay, so I've got my 2 little bullet points. The first one is that with the standard normal distribution, our mean is 0. And our standard deviation is 1. We're going to see, we're going to have to draw another little curve and going to put the numbers on the number line. It's the exact same way. Now it's more specific. It's not, hey, what is your mean? It's the mean is 0. Okay? So, and then my second bullet point is any x value can be transformed into a z-score. By using, and then I'm going to give you all the little formula that you use, which obviously I would give you all in the test, okay? Okay, and this is what it is. We have z equals, you take whatever x value you're dealing with, whatever x value you're told you have, you subtract your mean, and you divide by the standard deviation. Whenever we do 5.2, this formula is kind of going to change a little bit, okay? So to find your z-score, they give you an x, right? You subtract from that your mean and divide by your standard deviation. And then now right here, let's actually kind of draw this standard normal distribution. Very poorly drawn, but whatever. What is my mean? 0. Now when I go over one standard deviation and my standard deviation is 1, what I end up getting is just 1. And if I go over 2 standard deviations, I have 2. If I go over 3 standard deviations, I have 3. And then do the same thing going to the left. But if I'm at 0 and I subtract 1 standard deviation, I got a -1. Then I subtract 2 standard deviations, I got a -2, and then a -3. Okay, and then y'all, I always just kind of touch here, and I'm like, okay, try to, even though it's ugly and it's not drawn right, I try to make it to where, you know, these start at the approximate place there. It doesn't really work. I'm not going to have you draw one, so you don't got to worry about that. What's the area under here? So it's going to be the same area as it is with the normal curve for the normal distributions. Still going to be 1. And I got 1 example. I only think there was like 2 on the homework. I don't know. There's like 20 problems total, but there's a lot of definition, and then there was like 2 or 3 or 4 of each.
It'll be one. It'll be like 20, 21 quizzes. It'll be like 13.
Yeah, this one I think has 20. It had 43.
Dang.
So, I mean, free of charge, you're welcome. I cut it in half. Y'all, when it becomes so redundant, you know what I mean? It's like you shouldn't have to do the same problem 15 times. Like, I really think I'm trying to simplify it as much as possible to where y'all should be able to sit down, look at this, and answer it. I'm not listening to you. Ready? Example.
Wow.
I don't even know what you're trying to say, but I'm sure it can go without being said. Okay, y'all, example. I'm trying to read this, and I'm trying to think of it. I don't think it's wordy either. I think it just gives you the information that tells you to find the z-score, and then it tells you to interpret the results and to determine if it's unusual. So it's like an ABC, okay? So I don't know why I numbered it 1. It's the only one we're going to do, but I already wrote it. So mean is equal to 29.5. I have a standard deviation of 3.2. And what I'm going to do for part A is find the z-score when x equals 24. Do y'all see how the z equals, it's x minus mean divided by standard deviation? Oop. I just was given every single thing I need to just plug into that little formula. Okay. Okay, so that's part A, find the z-score. Part B is to interpret results. And then we have C. You could throw that away. That paper. And then C is determine if unusual. And I never taught this before, so I didn't know what unusual was at first, but whenever we get to C, I'll kind of explain to you, hey, this is why it's unusual. Okay? I'm going to switch to purple just to kind of break up the monotony. For A, find the z-score when x equals 24. Okay, well, I find the z-score by taking, By taking my x, subtracting the mean, and dividing by the standard deviation. My x is 24. I subtract 29.5, and I divide by 3.2. You could either do the numerator in your calculator and then divide by the denominator if you want to do order of operations by yourself, or you could go ahead and kind of get to that right here. Yeah, you could just go to the fraction button or whatever on your calculator allows you to have that n over d, that numerator over denominator. And then right here I have 24, subtract 29.5, go down and do 3.2. And I get negative 1.71875. Homework told me to round to the hundredths place. So I have negative 1.71875. Homework says round to hundredths place. Hundredths place would be this 1, but I look at the 8, and the 8 tells me to go up. So negative 1.72, that's my z-score. And then whenever we're talking about z-scores, negative z-scores fall below the mean, or like to the left side of the mean. A positive z-score would fall above the mean. Okay, so a negative z-score means that I'm going to be somewhere over here in this area. If I figure out what the z-score is and it's positive, then I would actually be falling to the right of the mean. This one falls to the left of the mean because it's negative. And so when it asks you to interpret it, I'm going to go ahead and interpret it right here. Long time now. Here. Okay. So this is how we would interpret it. Our x being 24 is about 1.72 standard deviations below the mean. Why would I be saying below again? Because my z-score was what? Negative. Negative falls below. Okay? A positive would be above. So if this is what I'm talking about, I'm about right here. This is about where I am, a negative 1.72. My mean is 0, right? So I'm literally falling below the mean. When my x equals 24, I'm about 1.72 standard deviations below the mean. I don't know why they didn't answer it negative. Our z-score being negative is what tells us it's below, but they answered it with just a positive. Maybe the absolute value, I don't know. We can look and see. We'll figure it out. I'm trying to think of how many of these there are.
And this is all for, this is for
That's just 5.1.
5.1.
I have so many pages left. There might be a little bit of time after class because I do have more pages to do. That if you have your laptop, I can pull it up on here and go to that problem and just kind of see. I just know that I have it as positive, and now you're making me doubt whether or not. We're going to stick with this because it's actually explicitly stating below. If I answered with a negative, then like that negative would be saying that it's below. So I'm guessing if it's saying the word below, it just wants like the absolute value of how far away it is. So not the negative sign, just how far away is it, and then you say below or above. Okay. Okay, and then C, as far as it's saying determine if it's unusual. So this is what I learned. So not A. Oh, I don't have my white out. The z-score, not a z-score. I'm just gonna scribble it, y'all. The z-score. That made you have to crumple it? I'm just kidding. The z-score falls between. I just said that, well, y'all should be in pencil. Right here. What did I say it was? I was about right here, right? With a negative 1.72. And that falls within negative 2 and 2, or like 2 standard deviations. And if it is within the 2 standard deviations, it's not unusual. If it's greater than 2 standard deviations on either side, then that's when you say it's unusual. I will. So the z-score falls between negative 2 and 2. Therefore, not unusual. And then right here we could say, therefore, not more than, damn it, Jennifer Nicole, I need to write up. Not, oh, here we go. Not more than, I had to add it, not more than 2 standard deviations away from mean. I should have put the mean there too. So if we did the z-score and we got like negative 2.89, that's more than 2 standard deviations to the left, below the mean, you would say it's unusual. Okay? So as long as it falls within 2 standard deviations.
How do you not choose 2?
I didn't until I got to the answer and read the description and opened up the PowerPoint and learned what to tell you. That was it. That's just what determines it being unusual. If it's more than 2. Here is not unusual because it's not more than 2 standard deviations on either side above or below. If it is more than 2 standard deviations above or below, then you say it's unusual. Okay? Okay. Now let's find the area. We have area and then probability. I wanted to stop at area and do our break, but our break isn't for a while, so I actually can keep going for a while. The only thing I don't like is how the homework will be like all over the place and do like all these different things. Okay. It was this one. Okay. So finding area under the standard normal curve. Yeah, that was like this one. Finally. Oh, it's hot in here. Finding area under the standard normal curve. I was thinking about my my fall semester coming up. I have developmental stats that I'm going to be teaching, and then I have a standalone stats, where everything I teach on 2.5 hours, they have to learn in 1 hour and 15 minutes. And I was like getting anxious. I'm like, how am I supposed to cover all of this and explain it in 1 hour and 15 minutes?
Just start by examples.
Right, that's used to, I can't talk today. That's how I used to teach college algebra. I would immediately just start doing examples instead of like trying to explain everything.
Just brief explain, and then the example.
More examples than anything. No, I like hardcore got anxiety. I was like, how am I supposed to do that? Because it's like a crash course. Well, I mean, I have like the videos and stuff, so I'd be like, hey, watch these. Like, we went really slow, so slow in my last class. Okay. Yeah, we're going to finding the area under the standard normal curve. So standard normal curve is the one where your mean is 0, your standard deviations are 1, and the area was 1. All right, but how we find the area whenever we're given a certain z-score. Okay, so, that's it. Okay, I got confused for a second. I break down how to find it if it tells you you're to the left of your z-score. I break down how to find it if it tells you you're to the right of the z-score, and I break down how to find it if it tells you you're in between scores. Okay, so first little bullet point right here. The way that we do this is you sketch, curve, and shade. And then left of z-score. What we do, if it says we're to the left of a z-score, is we use table. Okay, and here's an example. The area, and the homework straight up is like, find the area to the left of z equals, okay? So you're going to use the fact that it says you're finding area, and you're to the left of z equals 1.23. What did it say to do whenever we're to the left? Use the table. So here's the table. Standard normal distribution. So what we do, okay, so our z-score, that's a positive 1.23. You grab your table and you look at the positive z-scores. Okay, you've got positives on one side, you have negatives on the other. Okay, on the side that has all the positives, on the left-hand side where it says z, if you notice, the only thing that they have is to the 10th place, right? 0.0, but that's to the 10th place. 0.1, that's to the 10th place. My actual z-score goes to the 100th place. So start with the whole number, which would be 1, and you literally find 1. on your z-score. And then I look back at on your table, and then I look back at my z-score. It's 1.2. So I'm going to go down until I get to 1.2. The z-score I was given has a hundredths place of 3. Your hundredths place are all up top. So 1.2 I found on the left. Now the hundredths place I find up top. This hundredths place would just be 3. Okay? So with my left finger on 1.2, I go and I find 0.03. And now I'm going to bring them together. I'm going to match them. So I got 1.2 here, and I got 0.03 here. So there's 1.2. Here's 0.03. So let me get my finger just right. Okay, everyone should be looking at 0.8907. Okay, that is the area. That's it. Area equals 0.8. Because, okay, so on the left-hand side, the only thing I was given was the whole number, and then the tenths place. My z-score goes to the hundredths place. Your hundredth place comes from all of these columns right here. So you find your whole and your tenths on the actual very last digit would be why I went to the 0.03. Like if you add those together, right? If you add 1.2 with 0.03, you get 1.23. You got to find it on the table. That very, very, very last digit you'll find here. So but hold on though, because let me actually follow the directions that I gave y'all. Sketch and shape. Sketch, curve, and shape. So here's me sketching the, that's the most hideous curve. I'm standard normal, right? Mean is what? 0? And where is it telling me I am? Right now it says that I am 1.23. So standard deviation, I'd go 1 here. And it's going to be a little bit more than that. Just call it 1.23. So this is where I am, right? And am I to the right or to the left? The left. So what it wants is, what is the area right here? That's what it's asking. Remember, the whole area under the standard normal is 1. So what is that area? This area, from looking at my table, is 0.8907. This helps visual representation. Say you look on the table wrong, you've got all this stuff shaded, and it says your answer is like 0.0003. No, that's a way greater area than 0.000. Do you know what I mean? You can kind of just compare them. 0.8907, that's really, really close to 1, right? And if you look here, there's a whole bunch underneath that standard normal that's been shaded. Okay, so that's how you do it. If it's to the left of the score, just use the table. I sketch it, I look, I compare. If you pick up the table, you should get your answer. Okay, just pay attention to where it tells you to round things. Okay, now what about right of z-score? That's already the very first bullet, so that's going to be for sure what we do. Right of z-score, comma, use table, then subtract from 1. And now let's do the example. I want to find the area to the right of, and I noticed that on the PowerPoint, they just use the exact same thing, z equals 1.23. So I just did the same thing also. So if I don't remember, but it's not really, really hard to find, and if it's finding the table, it's probably a handful of these. Like, how many homework problems are there? I don't remember. It's like 22, 21, 22, 23. Oh, you should have, what did we do in 4.1, 4.2, 5.1, 5.2, and 5.3 all make up exam 3. So, but like for now, today, it's just 5.1. And 5.2 and 5.3. On Thursday, we're doing 5.2 and 5.3. Okay, so if I sketch this hump, that means what? Yeah, definitely for 5.2 and 5.3. I'm being dead serious to be here. I've already looked at it, and it's like, it's this, but like in a different way. This right here to me wasn't that hard. It's a lot, don't get me wrong. But the math itself, y'all, we literally just, we're going to take the number 1 and we're going to subtract the number from it. You know? Okay, so here I'm the area to the right. So that's all of that right there. And the way that we figure this out, if we use the table gives me at z equals 1.23, this, the 0.8907, right? But that is this much area. That's not this much area, which is why we have to do 1 minus, okay? Because we're technically subtracting the left-hand side, and that's what gives us the difference. So if you take 1 minus, after looking at the table, we just did it a second ago, which is why I'm not getting the table again, right? 1 minus, when you look at the table, you get that the area for z equals 1.23 is 0.8907. You put that in your calculator, and this area that we're talking about is actually 0.1093. To the left, just pick up your table. To the right, pick up your table, and then whatever value you get, subtract it from 1. 1 minus 0.8907. So, first step, sketch and curve. Sorry, just getting sketch curve, and then shade it, right? So when it says area to the right of 1.23, I drew a very poorly drawn curve. Here's 1.23. To the right, I kind of shaded to the right of that, right? There's only a little bit left underneath this curve. And I noticed that the directions for, if it said I'm to the right of my z-score, I use the table. So I find what is z equals 1.23. We had just found it, Dominique, right here. Right? And then it told me that after I use the table, subtract that value from 1. Yeah, big important step there when you're to the right. And then as far as the area is concerned, we also have whenever we're between 2 z-scores. So I'm going to kind of talk about what you're supposed to do there, do an example, and then I had 2 more examples just to kind of throw them out there. And then after that, I've got 3 examples finding probability, and then that was it, y'all. So to the left, use your table. To the right, use your table, but subtract that value from 1, okay? In between, meh. So I'm going to do the area in between in 3 minutes, and then we'll take a break, and then we'll come back. I'll do the little examples and then the probability, and then we'll be done, y'all. Okay, area between 2 z-scores. What's the shorthand for between? Isn't it B/ and then W? And then we're going to have to come up with something. Area between B/T or B/W. It's one of the 2. Between 2 z-scores. I'm sure there's probably already a shorthand because that's annoying to write over and over again. So this is what we do. If it tells me that I'm trying to find the probability between 2 z-scores, you find z-scores with the table, so you find each individual z-score, and then we subtract smaller from larger. Example. And so the problem itself says find the area between, and then it gives you 2 different z-scores. z equals negative 0.9 and z equals 1.3. Very first bullet we ever did was sketch the curve and shade, so I'm going to do that. I know that my mean is 0. And each time I scoot over a standard deviation, it's 1, but I'm specifically being given these values right here. If 1 is right here, it'd be, just shy of it. Because it's my own sketch, it doesn't really matter, but I do know it's to the left. That's the most important. Negative 9 is to the left of 0. 1.3 would be to the right of 0. Hopefully those words make sense. This is the approximate value. And I'm trying to figure out what is this area underneath the standard normal distribution. And I'll put my work in purple. Okay. So the area for z equals negative 0.9. I'm going to use my table. This goes to the 10th place. My left-hand side goes to the 10th place. So all I have to do is find negative 0.9 on my table, which I'm going to have to cover up, y'all. It's right here. If you notice, the numbers they start at negative 0, 0 on the bottom, go up to negative 0.9, and then I don't need anything after it. Don't use the one right next to it, because look at that 100th place. This is actually saying negative 0.99, and I want that. I want negative 0.9 what? 0. It's all the way at the end. So I get 0.1841. Kind of seems backwards compared to the flip side with the positive numbers. So just be careful when you're going along your columns on the top. So the area, when my z-score is negative 0.9, is 0.1841. And then we need the area when z is equal to 1.3. I'm going to go to the positive. I'm going to go to 1.3, and then that's it. Do you notice how right next to it, that's where my 0.00s are. So you don't keep going along with that very first one. Okay, the zeros are at the very end on your negatives. It's at the very beginning on your positives. Okay, so here's 1.3. I don't want anything else, so I stay right here in this column with the 0.00, and I get 0.9032. So I've used the table to find both of the z-scores. Now I subtract the smaller from the larger. And then I just wrote this. I don't really know if you'll see this, but this is just in my mind what makes sense. I'm computing a z-score in between these amounts. So like this is what I'm figuring out. And if I do 0.9032 and I subtract from 0.1841, I'm going to come down right here, y'all. What I end up getting is 0.7191. No. I subtracted a smaller number from a larger number. Calculator? The one's on a negative. I'm just subtracting. Well, it's 0.9, and I'm subtracting 0.1. So because that one's smaller than the 9, you're still going to end up with a positive. But literally, grab your calculator, y'all. 0.9032 minus 0.1841. I don't know what the heck. I had a weird exponent in there. 0.9032 minus 0.1841. I get 0.7191. Just reading it, it said to find the z-scores, subtract the smaller from the larger.
Oh,
That's it.
Way more difficult.
I'm just saying it in math.
Okay.
That's just, and because I wrote it here, I just wrote it here. You could just do what it says next, which is subtract smaller from larger. I'm finding the area between these two z-scores. And so, I just kind of wrote it like that. Because this table is giving me the area, right? the z-score. There. Subtract the smaller from the larger.
How do we get large digits in?
Whenever we found 1.3 on our table. So if you look at your table, right here, on the positive numbers, go to 1.3. And then if there's no other numbers after your 10th place, then that implies that there's just zeros. And if you notice in the top, it's 0.00, 0.01, 0.02. I want 0.00, which is just right there.
Okay.
Yeah. And then just be careful, because if you do more positives and negatives, you might get confused. But the 0.00 is the first column on your positives. On your negatives, the 00 is actually at the end. So you might just kind of think that you're just going with it and then like kind of mess up. So actually look up here and see what you're dealing with before you try to like put your fingers together and like pair them. Okay? Okay, y'all tell me what the z-score is for negative 1.75.